Yo, what's going on, class? Hope you're doing well. Today we're covering a new topic, still it's covering limits. Now we're only talking about one-sided limits. You understand what that means in a bit. Hopefully, by the end of this lesson, you'll be able to estimate the value of one-sided limits. Now, just a quick little review from what last time was. So in class, not the video. So we estimated the value of actually one of these limits. So x is approaching -1 of x squared minus 2x minus 3 over 3x plus 3. And so we're like, okay, well, the limit doesn't really care what's happening at -1. It only cares on what's happening on either side of it. Because either way, if I was to plug in -1 here, I would get 0 on the bottom. So we're like, okay, let's look at numbers that are smaller than -1 and then numbers that are bigger than -1. So smaller than -1. Well, I'm sorry. In this case, this is bigger than -1 here. We saw that as x was approaching -1, our f of x was getting close to -1.3. Okay, that's one side. As x was approaching -1 from the other side, we saw that f of x was also approaching -1.3, which led us to say, hey, the limit as x approaches -1 for this function is actually -1.3. Or you could say -4/3, however you like to say it. So that was, we used pretty nice numbers. We used pretty nice functions last time in class. I didn't get to this function, which I would love to. So what about this one? This is known as some people call it a step function. You don't really need to know that. It's just kind of like nice information to know. But it says the limit as t approaches 0 of h of t, where h of t is 0 if t is less than 0, and 1 if t is greater than 0. So then you're kind of like, okay, well, I don't really have like a function I can kind of work with here. I have like this piecewise / step function. So maybe it's easier if we look at a graph, okay? So here's a graph. This is saying here, h of t is 0. h of t is 0 if t is less than 0. So all the values of t that are less than 0, -1, -2, -3, so on and so forth, h of t is going to be on the 0. But h of t is going to be 1 if t is greater than or equal to 0. So we see this here. So how do I estimate or evaluate this limit? Well, we would have to do the same thing like we did last time, right? So we would have to look at the values for the limit that are less than 0 and greater than 0. And if we look at the graph that approaches 0 from the right side, it's moving in and let me get the laser pointer out. It's moving in and it's hitting 1, okay? But if we look at it from the left side, as it gets closer to 0, it's moving towards a y value of 0. That's weird. This one's approaching 1, this one's approaching 0. As opposed to the last one where they're both approaching -1.3. In this case, they're approaching two different numbers. But that kind of just contradicts everything we did last class. What does that mean? Well, in this case, the limit actually doesn't exist. So that little Mean Girls quote, it actually comes into play here. The limit doesn't exist. That's not problematic. That is possible. So don't freak out. I'm like, oh my gosh, it's possible. It makes sense. It makes sense. And so today, we're going to talk about that situation, that case, but only with one-sided limits. Now, I feel like I'm already talking so much here, so I wanted to bring in a special guest. He's a very busy person. I'll say that. It was hard to kind of schedule a time to get with him for him to come. He's always working. He has so much things to do, and so I wanted to bring in this special guest. He's a big fan of mine. I'm a big fan of his. Hopefully, he gets to share some wonderful insights. He's very knowledgeable. I'll say that. So let me pass it on to him. Well, howdy there, folks. My name is David Crockett, Texas hero, and if you don't remember me, you probably should have paid attention to 7th grade Texas history. Now, you may remember me from that famous Battle of the Alamo. Well, I'm somehow still alive. That Santa Ana didn't get to me today. Well, I'm a big fan of that Mr. Garcia fella. He was back then. He's actually not that young as he looks. He was back then with the Alamo with me, teaching my friend me and David Bowie some mathematics. It's crazy stuff, isn't it? So what we were discussing back in the day, and we decided to take a trip down memory lane. It's like we were discussing this thing called limits. Limits, you say? Which something you guys are doing right now. So I didn't know my limit back then, as in that Texas Alamo mission. Didn't know my limit back then, but now I know it now. So what are limits? We're actually going to look at a little thing called a one-sided limit. So one-sided, like in battle, we're going to look at a right-hand side and a left-hand side limit. You got it? Okay, cool. You know what? You know, Mr. Garcia is such a nice fellow. He gave me a little pointer thingy. Let me see if I can find it somewhere around here. That's not it. Is that it? That's not it. Oh, here we go. Look at this little contraption. I don't know what it does. Doesn't really help me in battle, but looks kind of cool. So we're gonna look at two little things called a right hand limit and a left hand limit. Okay, okay, okay. Good. So our right hand limit. You already know its notation. LIM, that means limit. X approaches A, you already know that as well. And f of x now, you already know that as well. You guys are so smart. This little thing that's new is that little plus sign right there. Maybe it would be better to do this. The little plus sign right there. That means right hand side. So when I say all this, I'm going to say the limit as x approaches A from the right hand side of f of x equals L. I'm going to say that one more time for you. I'm going to say that one more time. The limit as x approaches A from the right hand side of f of x equals L. Okay? Okay. So when we look at that one question, we're only looking at the x's that are greater than A. Alright? So the x's that are greater than A. I know you may be thinking to yourself, but that's only for greater than A. What about if they're less than A? You know what? My grandpappy always taught me that. If you're always thinking about the opposite, probably should do the opposite. You're always thinking about the not opposite, probably should do the not opposite. Alright? These are very, very lessons from my grandpappy. Now, the famous lesson from David Bowie as well is the left-handed side as well. Now, the left-handed limit, as you can see, it's very familiar. I'm just very comfortable here. The left-handed limit is very similar. Okay, so the limit as x approaches A. Ooh, what is that? That's a negative. Oh, well, okay. Well, it's the limit as x approaches A from the left-hand side of f of x equals. I'm gonna say that one more time for you. I'm gonna say that one more time. The limit as x approaches A from the left-hand side. Not necessarily mean it's gonna be negative. It's just approaching from the left-hand side. Same thing for this other fellow over here. It's approaching from the right-hand side. It doesn't always have to be positive. Okay? Okay. So that means here, for these values of A, we want them to be less than x. Alright? So we care about the x values that are less than A. Alright? So right hand, want them greater than. Left hand, well, they stand. So that means here, fellas, we got some work to do. Okay? We need to see, what does that mean? What does it look like? How does it affect the limits altogether? Well, and I would love to stay. Here's the thing. But I got myself an appointment with Mr. David Bowie. We got to go and take care of some stuff in Austin. You see, now it's a long trip on our buggy, so we got to get going. We got to get going. I'm gonna take this from Mr. Garcia. Hopefully he doesn't. Doesn't. No, no, no. We're good, Mr. Garcia. Wait, we're just finishing up. We're just finishing up, sir. This one is. What is such a kind fella. Well, I bet's been going. Got myself a long day coming. Better take me a siesta. Adios. All right, man. What a very special guest, Davy Crockett from Texas history, very famous legend. I'm glad he's able to stop by. He's a very big influence on my life. Him and David Bowie, not the musician, but like the actual David Bowie. So thanks. Give it applause right there in your house, just like very nice applause. If you have a Texas flag, make sure to get that out and wave that high. So let's kind of see what was David, not David, what was Davy talking about? Um, there are two different types of limits that we're going to learn about today. Laser pointer, cool. We have a right-handed limit and a left-handed limit. So we used the same definition last time just for limit. So I'm going to modify it just a little bit, okay? So we're going to say the limit as x approaches a from the right. That's how I say that. All right, so the limit as x approaches a from the right of f of x equals L. And this is the same, literally the same wording as last time, provided we can make f of x as close to L as we want for all x sufficiently close to a with x being greater than a without actually letting x be a. Again, we'll emphasize that last part near the end. But this is the biggest change. Instead of focusing on my a value from both sides, whenever I have the limit as x approaches a from the right, I'm only focusing on one side. And then vice versa as well. Whenever we have the limit as x approaches a from the left-hand side, I'm only caring about one side of my limit. So let me have it here. I think it's here. Yeah. So a couple things here. That change in notation is very minor. One of it is the right-hand side, it's a plus sign, and one of it is the left-hand side, a negative. You'll see here that is so important to get that distinction down because your answer can be completely different. We'll look at a couple examples to show us how it can be completely different, but our answer can be so but different. And just as Davey said, when I'm talking about the right-hand side, I'm looking at the values that x is greater than a. And when I'm saying left-hand side, I'm looking at the values of x being less than a. So then practically speaking, oh, that sucks. Whatever. So I should have done animations, but whatever. When we estimate the value of this following limit, again, the one I just gave you earlier, I'm going to modify the question a little bit. Instead, I'm going to ask you to find a limit as t approaches 0 from the right of h of t, and the limit as t approaches 0 from the left of h of t, where h of t is this step function or slash piecewise function. And again, if I'm evaluating just this first one, a limit as t approaches 0 from the right, that means here's 0. I want to look at the values of t that are greater than 0. Obviously, 1 is bigger than 0, 2 is bigger than 0, 3 is bigger than 0, so on and so forth. So I'm looking at this part here, the values of t that are bigger than 0. What is that limit? Well, it looks like as it approaches 0, it's approaching 1. Okay, so we have this limit as of t as the limit as t approaches 0 from the right of h of t is equal to 1, as opposed to the limit as t approaches 0 from the left, because from the left is the values of t that are less than 0. And my values of t that are less than 0 are these negatives down here, but these negatives are approaching 0 as well. So that means the limit as t approaches 0 from the left of h of t is actually 0. So once we make this distinction right here from like the right-hand side and left-hand side, we can actually get two different answers for the limit. Now, we'll talk about more, actually I think it's on the next page here. Yeah, this next page here. Well, actually, it's in a bit. Yeah, it's in a bit. Again, just like with the other limits, one-sided limits don't care about what's happening at the point any more than normal limits do. All right, they're still only concerned with what's going on around the point. Okay, the biggest difference between one-sided limits and the normal limits is the range of x's that we look at when determining the value of the limits. That's just about it. Now, a big little summary. This is going to be like if you want like a very precise mathematical definition. So given a function f of x, that if the limit as x approaches a from the right, if that equals the limit as x approaches a from the left, just the normal limit will exist. So if the right-hand side limit equals the left-hand side limit if those are both the same number, well, then that means the limit exists. Same thing, that if the limit exists, that means that the right-hand side limit and the left-hand side limit must be equal. And it also kind of like vice versa, in the sense of if two one-side limits had different values, as in the limit from the right-hand side and the limit from the left-hand side had different values, that means the normal limit does not exist. So very similar to what we saw on that last question with the piecewise. The limit from the right was 1, but the limit from the left was 0. So yeah, that's awesome that the right is 1, and that's awesome that the left is 0, but the limit as t approaches 0 does not exist. So that may seem a little bit confusing. We'll look at some examples to kind of help solidify that concept. So is this example? Okay, cool. So given this graph, we're going to compute the following limits. I want you to compute f of -4, the limit as x approaches -4 from the left, then -4 from the right, and then just -4 altogether. So here, f of -4, I mean, this is not a trick question. Find f of -4. So that means when x is -4, what's my corresponding y value? Okay, so here on my graph, well, we got a -4 right here. There's an open dot right there. So since there's an open dot, regardless of a little discontinuity, this would actually mean f of -4, I shouldn't say equals, my bad. But f of -4 does not exist. I'm going to say D and E, so if you didn't know, does not exist. It's the same thing as D and E. Just easier to write, you know. The reason why, again, there's an open hole there. There's not a closed dot, but that is the f of -4. Now the limit as x approaches -4 from the left. Again, if we're approaching from the left, that means I want to look at the values in -4 that are less than that. You get the pointer. Excuse me. So the values of -4, so the values that are less than -4 are on this side here. So -5, -6, -4.5, so on and so forth. So as we get closer and closer to -4 from the left-hand side, looks like we're approaching 2. Excuse me. Looks like we're approaching 2. Okay, so that equals 2. Now, we need to find the limit as x approaches -4 from the right-hand side. So right-hand side, again, is the values that are bigger than -4. So as I approach from the right-hand side, it looks like I'm getting closer to 2. So it looks like it's also 2. So, like we said on the last page for the summary, if the left-hand limit and the right-hand limit both approach the same number, that means the limit altogether, the normal limit, exists and is that same number. Biggest thing again, yes, f of -4 does not exist. That is true. However, the limit as x approaches -4, that does exist. That is positive 2. The limit does not care what happens at that point, but it only cares what's happening around the point. Let's look at another example. F of 1, the limit as x approaches 1 from the left, from the right, and then just 1 altogether. So the limit as, the f of 1. Find out where your x is 1 and find your corresponding y value. Now, what is this here? This is fun, isn't it? We have a positive 4 right here, so a closed dot. That's nice. We love that. You got an open dot down here. So think to yourself, answer this question out loud if you want to. F of 1 is the answer 4, -2, or does not exist. I want you to give an answer, have it in your thought before I say it. Is it 4, -2, or does not exist? You're right. It is 4. The closed dot takes precedent over the open dot. It there exists a corresponding y value when x is 1. So let's find the limit as x approaches 1 from the left. So that means the values of 1, sorry, we want to look at the values that are less than 1. So these numbers over here. So as I approach 1 from this side, it looks like I'm getting closer to 4. Okay? As I approach 1 from the left-hand side, looks like we're getting closer and closer to 4. Okay? So the limit as x approaches 1 from the right-hand side. Oh, this is different, isn't it? Because the limit as x approaches 1 from the right-hand side, that means look at the numbers that are bigger than 1, and which are, these numbers here. And as I approach 1 from the right-hand side, I'm getting closer and closer to -2. So, the limit as x approaches 1 now. So when we look at the limit as x approaches 1 from the left and 1 from the right, those are two different limits. They're not equaling the same number. So that means the limit as x approaches 1 altogether of f of x does not exist. The left-hand limit does not equal the right-hand limit. Therefore, the normal limit does not exist. One more. F of 6, and then 6 from the left, 6 from the right, and then just 6 altogether. So f of 6 here, again, open dot, which is on the graph too, but there's a closed dot down there. So what does that mean? That means f of 6, I'll give you three choices again. Is it 5? Is it 2? Or is it does not exist? Again, give it a shot. You're correct. It actually would be 2. And if you haven't already, try this last part by yourself. You can pause the video if you like. I just want you to try it by yourself before we continue. So the limit as x approaches 6 from the left-hand side. Again, since it's from the left-hand side, that means you look at the values that are less than 6. So this side right here. So as I approach 6 from the left-hand side, let's say I'm getting closer and closer to 5. Okay? So the limit from the left-hand side is 5. What about the right-hand side? That means the values that are bigger than 6. So I approach 6 from the right-hand side. Looks like I'm getting closer and closer to 5 as well. Okay, cool. That's nice. Oh, that's not good. Perfect. And then finally, hey, left-hand limit exists. Right-hand limit exists. They're both going towards the same number. This is good because the limit as x approaches 6 would now equal 5. Again, f of 6 was 2, but the limit as x approaches 6 was 5. F of 1 was 4, but the limit as x approaches 1 did not exist. And f of -4 did not exist in the first place, but the limit as x approaches -4 was 2. The limit does not care what's happening at that point. It only cares what's happening on the around the point. I think I said that here. Yeah, when dealing limits, remember, they don't care about what the function is doing at the point in question. They're only concerned with what's happening around the function, around that point. I think we have another example. So you will have Delta Math homework over this, and literally just pull this question straight from Delta Math. So this is an example of a question you may receive. Obviously, different numbers, different graph, altogether, it's all randomized. So if you get this question somehow in your Delta Math, nice. Good job for you. But it's very similar to what we did last time, okay? So f of 4. So let me get my laser pointer out. Actually, cool. F of 4. We have here at x equals 4, open dot, and a closed dot. All right. So we've done 2 of these examples already, so I won't waste too much time. F of 4 here, would actually be, you're correct. F of 4 here would actually be negative 5. It wouldn't be negative 2 because there's an open knot. It would be negative 5 because there's a closed knot. Okay, cool. So as you approach 4 from the left-hand side, so that means the values that are less than 4, so all this stuff over here, what are we approaching? So as we keep going this way, keep going this way, oh, hi, open knot. Looks like we're approaching negative 2. So this here, negative 2. Okay, what about if you're approaching from the right-hand side? So the values of 4, sorry, the values that are bigger than 4. So here, laser pointer. So as we approach 4 from the right-hand side, looks like we're getting closer, closer to negative 5. Uh-oh. We're approaching 4 from the left, and that was negative 2. And we're approaching 4 from the right, and that's negative 5. Therefore, the limit as x approaches 4, what is it? Correct, does not exist. Why does it does not exist? Because the left-hand limit and the right-hand limit are not the same. I think that was the last slide, right? Yeah. So then I do want to emphasize again this summary page. If the limit as x approaches a from the right equals the limit as x approaches a from the left, that means the limit exists, and it's that same number that they're equal to. And same thing, but in the opposite direction. Well, not really the same thing. Um, if the limit as x approaches a from the right is not the same as approaches it from the left, that means the limit does not exist. All right. So this was just a kind of different way to view limits. Um, you'll have homework over this. It'll be all on Delta Math, and we'll do some more practice in class on Thursday. If you have any questions, please let me know. If not, y'all have a great rest of your day. I'll be sure to tell Davey that he needs to work on his accent. It sounded like George Bush with Barack Obama there for a second. So I'll be sure to tell him that.